Howdy, today I'm Flippin Science looking at changing reaction rate by changing temperature, surface area, and using enzymes and catalysts. So the science understanding that we're going to look at, we're going to use collision theory to explain changes in reaction rate due to temperature, surface area, and catalysts, and that includes inorganic and biological catalysts, which are called enzymes. So let's just go back over what a chemical reaction is. To get a chemical reaction to occur, you need to have your reactant particles colliding with each other in the correct orientation with the right amount of energy. What we mean by that is when they're colliding with the right energy, that's enough energy to break the bonds between the reactants. So in our example here with hydrogen and oxygen, we need to break the covalent bonds between the hydrogen atoms and between the oxygen atoms to get the reaction to occur. So we need to provide that activation energy, and that's the energy that the particles have, and it's kinetic energy because they're bouncing around and they're bumping into each other. They also need to collide in the correct orientation. That means facing in the right direction when they hit. That means that if they collide with the right direction, then they break those bonds, and that leads to the reaction as well. So let's start by looking at the effective temperature. So the effective temperature, we can use some results from the sodium thiosulfate hydrochloric acid reaction that we had in the previous video. So you had sodium thiosulfate to hydrochloric acid, sulfur is produced, and that obscures a cross that's underneath the reaction vessel. And the time taken for the cross to be obscured is what we measure. So we can see as we're increasing the temperature, the concentration of thiosulfate is changing the same. The only thing we're changing is the temperature, and we're measuring the time taken for this cross to be obscured. From that we can calculate a rate by doing 1 divided by the time. So let's do that for the first one. So we've got 1 divided by 230, so 1 divided by 230, and we get 4.34 times 10 to the minus 3. So let's pop that in. 4.34 times 10 to the minus 3. Let's do the next one. So 152, so 1 divided by 152, and we get 6.57, 6.58 times 10 to the minus 3. So 6.58 times 10 to the minus 3. I'm going to do the rest now quickly. So now we've got our table, let's have a look at our graph. So the first graph we're going to look at is just the temperature versus the time. So we can see as the temperature increases on our x-axis, the time taken for the reaction to occur decreases. And we get a nice little curve here. Now let's have a look at the graph of the effective temperature on rate. We can see as we increase the temperature, the rate of the reaction increases as well. So let's have a look at an explanation for why we see this. So we can see as the temperature increases, the rate of reaction increases. And the reason for that is when you increase temperature, you're increasing the kinetic energy of your particles. So down here we can see that. So as you increase the kinetic energy of the particles, they move around more. There's two things that we can talk about here. The first thing is that there's going to be more collisions between the reactant particles where they have the correct activation energy for the reaction to occur. Since on average the particles have more energy, that means more particles are likely to have the activation energy for the reaction to occur. So that means that there's more successful collisions in terms of energy, activation energy. The other way of looking at it too is since the particles are moving around more, they're more likely to collide with each other. So you're going to get more collisions between the reactant particles per unit time. So what that means is statistically you're more likely to have collisions between the particles, and therefore the likelihood of successful collisions increases as well. So when you increase the temperature, you increase the number of collisions, and therefore the number of successful collisions per unit time, and therefore the reaction rate. And you also increase the number of particles with the required activation energy for the reaction to occur. So you get more successful collisions per unit time and a greater reaction rate. Now we're going to have a look at the effective surface area on the rate of reaction. In this case, we're going to use experimental data again. We've got hydrochloric acid, and to that we're going to add some marble chips, so calcium carbonate. The calcium carbonate is going to come in two sizes here. We're going to have large chips and small chips. As we add the calcium carbonate to the hydrochloric acid, we get a reaction occurring. We get carbon dioxide gas being released. Carbon dioxide gas can go out into the atmosphere, and that reduces the mass of what we have on the balance down here. So let's have a look at our results. So here's our graph. Here we have our time going on. Here we have the mass lost, and we can see for our large chips here, there's a smaller mass lost initially, and with our small chips we have a greater mass lost initially. Eventually they both react because we have excess hydrochloric acid, and there we go to completion, but the reaction rate for the small chips is much faster because we have a much steeper slope here than we do here. So the explanation for this is if we have a large chip, so we're going to use a cube for example, the surface area exposed is these 6 sides. and they have a certain surface area. If we have the same mass of chips, so taking up the same amount of space, but we cut it into smaller pieces, now we have extra surface area exposed for each of the edges on the outsides around here. So here we only have 6 surfaces, here we have many more surfaces. What that means is the more surface area you have exposed to your reactant, that means the more collisions you get between your reactant particles and the surface area, and that increases the reaction rate. So for our example, we're using acid and calcium carbonate. If we have smaller pieces of calcium carbonate, there's more surface area of calcium carbonate exposed to the hydrochloric acid, and that means you're going to get more collision between the hydrochloric acid and the calcium carbonate, and therefore you're going to get a faster reaction rate. Here's an example with lycopodium powder. Lycopodium powder is quite flammable. When it's in a big pile here and you touch a flame to it, however, it doesn't really catch on fire very readily. And that's because the surface area being exposed to the flame isn't particularly high, it's just the surface of the powder. Whereas if you blow it, you expose the surface area of all the pieces of lycopodium powder. That makes it catch on fire much more readily, and you get really spectacular explosions. This can happen industrially too. So here are some examples of some fine powder explosions. This is an explosion in Georgia in the US. This is a sugar factory. Underneath the silos there was a belt that takes the sugar to the processing warehouse. There was a blockage in there that caused a bit of dust to build up, sugar dust to build up, and there was an ignition source, probably just sparking from the conveyor belt, and that led to an explosion. The initial explosion led to shaking of the packaging warehouse, which led to sugar that was just sitting on the ground and on surfaces also going into the air, and any flames going past would catch those on fire and cause explosions too. This is a similar explosion that happened in the US early on. This is just stereograph. This was a flour mill. Flour mill silos these days are designed so that the top can blow off, and that contains the explosion in some way. It directs the explosion up and away from usually where people are going. This was a mine disaster in Australia at Mount Milligan. It was coal dust, so coal dust in the air caught fire. There was a huge explosion and it killed a lot of people. So if you have smaller particle sizes, that means you have an increased reaction rate because there's more particle surface area exposed to your reactants. That results in an increase in the number of successful collisions between the reactant particles per unit time between the reactants, and that leads to more product being produced in a shorter time, and that increases the reaction rate. This is used in all sorts of industries. This is a ball mill. This is used in refining mine products. Inside here you have steel balls that when you rotate this, that swings around, and that crushes up the rock that you insert on one side into a very, very fine powder. So that when you're trying to get metals out of that rock, there's a large surface area, so that increases the reaction rate, and it saves the company money because they can process the rocks much faster. The last bit we're going to talk about is catalysts. So a catalyst is a chemical that alters the rate of a chemical reaction but is not consumed in the reaction itself. Catalysts can either speed up or slow down a reaction. We're going to just focus on catalysts that speed up reactions. So this is a catalytic converter from a car. So in a catalytic converter you have usually a couple of catalyst beds. There's different catalysts in there that do different reactions. One's platinum usually, and one can be rhodium. The exhaust gas comes in, it passes through the catalyst bed, which has a really large surface area, which links to what we just talked about. And as it passes through it, reacts, and then safer gases come out the other end. So inorganic catalysts are metals or salts which change the rate of reaction. And that's what we saw in the catalytic converter there, where we had metals like rhodium or platinum. The way they increase the rate of reaction is they reduce the activation energy required for a reaction to occur by providing an alternate energy pathway. So if we have a look at a graph down here, we can see we have energy of reactants, energy of products. If we don't have a catalyst present, the activation energy, that's the energy you need to provide for the reaction to occur, is quite high. If you provide a catalyst, then you lower the activation energy required for the reaction to occur by providing this alternate pathway. That means that with whatever energy you have present, is the likelihood of the reactant particles having the required amount of activation energy is higher, since the activation energy is lower, so you have more particles with that activation energy. That kicks off your reaction and your reaction rate increases. For many catalysts, we don't know how the alternate energy pathway provides a lower activation energy. We don't know, for example, how platinum increases the rate of reaction in a catalytic converter. But we know it does, so we use that. So these are inorganic catalysts, metals or salts. Biological catalysts are a little bit different. They're made of protein and they're present in your body, in your cells, every single one of your cells, and we call those enzymes. Enzymes we use to do industrial processes by using organisms to do things for us. So making wine and beer, we use the enzymes present in a yeast fungus. Making cheese, we use bacterial enzymes. Bread dough, that's the same as the wine and beer. And tenderizing meat, we can use an enzyme from pineapple called bromelain. Again, the way they work is by reducing the activation energy required for the reaction to occur, and we'll have a look at how that works. Problems with enzymes is that because they're biological, they're affected by pH and temperature, and we're going to look at how that happens a bit later on. So the way an enzyme works is they have a shape on them called an active site. This is not representative of reality really, it just gives you an idea. So in this case we have our reactants. They merge at the active site. When they do that, the enzyme changes shape a little bit, and that forces the reactants together in this case, or it can force them apart in different cases. When the enzyme changes shape, it forces the reactants to react with each other, and then you get your products being produced. And this can happen really quickly. So there's enzymes in your body called ATPase. They work about 50,000 times a second each. So the way that this works to increase the reaction rate is there's two things that you need for a collision to be successful. You need to collide with the correct activation energy and the correct orientation. The enzyme provides the correct orientation. As the particles, the reactant particles make into the active site, they're forced to be in the right place. And then the small amount of stress that's applied by the enzyme is enough to make the bonds break or reform and produce your product. So by providing the space and the correct orientation for the reaction to occur, the reaction occurs much quicker, so you get more reactions per unit time, so therefore you increase the reaction rate. So let's look at some questions. The first question says, solid oxygen bleaches produce hydrogen peroxide in water. Explain why the rate of production of hydrogen peroxide from oxygen bleaches increases as the temperature of the water increases. So as the temperature of the water increases, the molecules present have more kinetic energy. That means you're going to get more collisions between the reactant particles to start with, so there's going to be more collisions per unit time, and therefore on average there's going to be more successful collisions per unit time, and that's going to increase the reaction rate. The other aspect is the collisions that are occurring have more energy, since you're increasing the average energy of all the particles by increasing the temperature. So the particles are more likely when they collide to have the activation energy required for the reaction to occur, which leads to more successful collisions per unit time, and that increases the reaction rate. So our second question, we're looking at detecting soil acidity by using hydrogen peroxide. A sample of soil containing iron sulfide is dried, ground finely and shaken with the hydrogen peroxide. Suggest one reason why the sample of soil was ground finely. So by grinding the soil finely, you're increasing the surface area of the soil, and that means the amount of surface area exposed to the hydrogen peroxide increases, and that will increase the reaction rate. So the last question talks about the production of polythene, which is a plastic. The industrial process uses high pressure and the use of a catalyst. State one advantage to the manufacturer of using a catalyst in the process and give a reason. So one advantage of using a catalyst is you don't have to provide as high temperatures or even as high pressures if you have a catalyst present, since the catalyst will help increase the reaction rate by itself. So by having a catalyst present, you increase the reaction rate since you have collisions between the reactants and the catalyst. The catalyst provides an alternate energy pathway of lower activation energy, and that means you don't need to have as high temperature or pressure for the reaction to occur, and that saves the manufacturer money, since they'll still produce the same amount of product, but they can do it at a lower temperature or pressure, which they don't have to pay for in terms of energy. So today on Flipping Science, we looked at change the reaction rate in terms of temperature, surface area, and the presence of catalysts or enzymes. That's it for Flipping Science today. See ya!